Electrochemistry. A battery is a great example of the power of electrochemistry. A battery, inside the battery, has these chemical reactions, and on one end of the battery generates a lot of electrons. So hook up that end of the battery to a wire, it could do some useful work along the way as it travels to the positive end of the battery. Aluminum is a common metal that we often recycle, and the reason why we recycle it is because when you do electrochemistry to get aluminum out of the ground from alumina, you plate it out, it takes a lot of electricity to do that, so it's very expensive. That's why we recycle. And we're going to see later that electrochemistry can be used in a lot of these sensor materials to sense the presence and the concentration of different chemicals. We've seen apples and some other fruits, they turn brown after you cut them, and the reason for that is an electrochemical reaction through an enzyme, polyphenol oxidase. And you can destroy that enzyme and prevent that browning from occurring by decreasing the pH. So maybe dip the apple in some lemon juice or something and destroy that enzyme, and you can really slow down the browning process. Electrochemistry is all about the transfer of electrons between reactants. So if one reactant produces 2 moles of electrons, the other reactant had better accept 2 moles of electrons. So to keep track of all these electrons, we assigned oxidation states of atoms in a compound. So let's review this. I don't know if you remember, but for example, you had a compound like carbon monoxide. What were the oxidation states of carbon in that compound? What's the oxidation state of oxygen in that compound? Well, we had 3 rules that we pretty much used to figure these things out. Let's take a look at the first one. Oxidation state of oxygen in a compound is always -2. The oxidation state of an element in its natural state, for example, oxygen gas, iron solid, right, aluminum solid, hydrogen gas, when in their natural state, an element all by itself is always 0. That's our baseline. When the oxidation states of all atoms present in a compound or ion are added, so you add up all these oxidation states of everything present, the total is always the overall charge. So let's try a few. We have carbon monoxide. Okay, let's see if we can get the oxidation state of everything. Oxygen is -2. I'm going to circle my answers here. Oxygen is -2. Carbon has to be +2 because there's no charge, so they have to add it to be 0. What if we had something a little more complicated, like nitrate? So we have oxygen is always -2. Each oxygen is -2. Well, what is nitrogen going to be? We have 3 oxygens. 3 times -2 is -6. So whatever nitrogen is, you have to add it to a -6, and you better get a -1 because the charge is a -1. So nitrogen has to be +5. Let's do one last little test. Let's try this. Calcium oxalate. See if you can figure out what the oxidation state is of everything in there. Okay, there's a couple ways to do this. One is to know that this is oxalate. So that means you could figure out the oxidation states of carbon and oxygen using this formula. Okay. Another way is calcium is in group 2 in the periodic table, so they all have a charge of +2. But either way, calcium has to be a +2. Each oxygen is a -2. 4 times -2 is -8. Okay, so what is each carbon? But I have 2 of them. So you could write an equation if you want. the overall charge is 0 for this thing. The overall charge is 0. That has to equal 2 plus 2x. If x is the oxidation state of carbon, I have 2 of them, plus a negative 8. So bring the 8 over there, positive 8 minus 2, positive 6, equals 2x. X is 3. Each carbon is positive 3. I think it's a lot easier to work with the ions, a lot easier, because we know each oxygen is negative 2. 4 times negative 2 is negative 8. So each carbon has to be what? You need a positive 6 here, because positive 6 and negative 8 is my negative 2. So that works. That means each carbon has to be a positive 3. So it's kind of easier to arrive at answers when you just know the charges of everything. Oxidation and reduction terminology, a little review. The thermite reaction is used to join railroad tracks.
Aluminum metal is a very strong reducing agent. The flower pot contains thermite, a mixture of finely ground aluminum metal and iron 3 oxide, plus a starter mixture containing magnesium metal. The reaction is initiated by igniting the magnesium metal ribbon. Some of the molten iron has flowed out through the bottom of the flower pot into the bucket of sand.
So electrochemical reactions can be very energetic, but this is the thermite reaction. Determine the oxidation state of everything in there. Okay? Let's try it. So the two easy ones are aluminum and iron solid. That's aluminum in its natural state, iron in its natural state. So there's my answers for aluminum and iron. Let's start over here. Remember, oxygen's always negative 2, so each oxygen is negative 2. 3 times negative 2 is negative 6. So each iron has to be what? Well, the total has to be positive 6, because it has to add up to be 0, because there's no charge. Each iron has to be positive 3. Over here, each oxygen is negative 2. Circling my answers here. 3 times negative 2 is negative 6. Same story. That side has to be positive 6. So that means each aluminum, since I have 2, has to be positive 3. When an element gets reduced in a reaction, its oxidation state gets reduced. Its oxidation state gets more negative. It's reduced. It's getting lower. When an element gets oxidized in a reaction, its oxidation state gets oxidized. It gets more positive. Oxidizing agents and reducing agents are always reactants. So an oxidizing agent is a reactant. A reducing agent is a reactant. And how do you tell them apart? Reducing agents always get oxidized. And they're always reactants. We already said that. Oxidizing agents always get reduced and are always reactants. Okay, so in the above reaction, what's the reducing agent and what's the oxidizing agent? Take a look at aluminum. It starts out with an oxidation state of 0 and it goes to positive 3. So aluminum got reduced or it got oxidized. But from 0 to positive 3, it got more positive, it got oxidized. So if it got oxidized, aluminum must be the reducing agent. The oxidizing agent has to be the other compound, but let's prove it. Iron, now oxygen, notice it didn't change. -2 to negative, well, -2 is -2. The oxygen doesn't change. But the iron went from +3 to 0. So iron got reduced, right? It got more negative. +3 all the way down to 0. It got reduced. So this compound, it got reduced. It is the oxidizing agent. Okay. Write the unbalanced half reactions for the thermite reaction. So all we're doing is half reactions is identifying each reactant and then what it went to. For example, we've got iron 3 oxide, and what did it go to? It went to iron. In the other half reaction, we have aluminum going to Al2O3, aluminum oxide. Aluminum going to aluminum oxide. Okay, so that's how you start with writing the half reactions, the unbalanced half reactions. Well, they want unbalanced. So those would be my unbalanced half reactions. But what if I wanted to balance them? Remember how to do that? First, balance everything but oxygen and hydrogen. So I would put a 2 in front of the iron. Now my irons are balanced. Balance the oxygens by adding water. 3 of them. Balance the hydrogens by adding H+. 3 times 2 is 6. Now you balance the charge by adding electrons to the most positive side. I have a +6 over here. I have 0 over here. So I have to add 6 electrons to make it the same charge on both sides. Try the bottom one. Start out by balancing everything but oxygen and hydrogen. So balance the aluminums. Now you balance the oxygens by adding water. 3 oxygens. So balance 3 waters. Now you balance the hydrogens by adding H+. 6 hydrogens, 6 hydrogens. Now the charge by adding electrons to the most positive side. Multiply the coefficient times the charge. 3 times 0, 2 times 0. This side's 0. The other side, 1 times 0 plus 6 times 1. This is +6. So I have to add 6 electrons over here. So one reaction is consuming electrons while the other half reaction is producing electrons. So can you see that the reducing agent gets oxidized? The reducing agent gets oxidized because it gives up electrons. The oxidizing agent, this compound, reacts with electrons and gets reduced. There's 2 types of electrochemical cells. The first is non-galvanic.
A pickle is incorporated into a simple electrical circuit. The forks provide contact between the pickle and the power source. Alternating current will be passed through the circuit.
So non-galvanic cells, it's like plugging a pickle into the wall socket. So you have to force it to happen. You can't make a battery out of that. This type, galvanic cells, are much more useful. They happen naturally. These electrochemical reactions occur naturally. You can produce electricity, like a battery. Let's make a battery out of lemons.
This lemon battery is related to the zinc-copper cell. You can build this battery from lemons, galvanized nails, and pennies. How much electrical potential is generated by a 3-lemon battery?
I don't know if you noticed, but this is called a voltmeter. This is a voltmeter that measures the volts, and it's reading 1.561 volts. So that's about a AA battery, so that's pretty good. So what are the reactions in the lemon battery? We had galvanized nails, or those galvanized screws contain zinc, and they are dissolving and producing zinc ions. Now these are half reactions, so we have to involve electrons. So add electrons to the most positive side. We need 2 of them because we need to have the same charge on both sides. The other half reaction is reacting with electrons. It's consuming electrons. And there, we're actually, when you put those copper pennies in the lemon battery, some of those copper ions actually dissolved. And they plate out into copper solid. So to finish the half reaction, we need 2 electrons. So there's my 2 half reactions for the lemon battery. So what would it look like if we separated the lemon battery half reactions into 2 different containers? Okay, something like this. Let's take a look.
A galvanic cell consists of 2 half reactions connected by a salt bridge and an external wire. In this example, a zinc metal electrode is oxidized to zinc ions at the anode, and Cu2 positive is reduced to form copper metal at the cathode. If the 2 half reactions are connected through a voltmeter, we can measure the electromotive force for the reaction. When connected to a light bulb, the current of electrons flowing through the wire causes the bulb to glow. The anions and cations flow through the salt bridge to compensate for the change in the charge caused by the electron flow.
Okay, the oxidation half reaction, the anode always produces electrons. Right? We're producing electrons. So this is my anode. It's the oxidation half reaction. Notice how we start out with a charge of 0, zinc oxidation state's 0, and then the oxidation state goes to +2. So that's oxidation. So the oxidation half reaction always produces electrons. Things get oxidized. That's the anode. So by convention, the anode is always placed on the left in the voltaic cell. So the anode is always over here and is producing these electrons. So electrons are going to flow from this side to this side, which is left to right. That's the convention. Always put the anode on the left-hand side. Okay, let's try drawing a conventional voltaic cell diagram for the lemon battery. And what that means is we want to make something look like this. That's a little more artsy than I can draw, but we'll try. So let's write our reactions over here. That will help guide our efforts. So we had 1/2 reaction of zinc solid going to zinc ion and 2 electrons. We had another half reaction of copper ions reacting with 2 electrons to produce copper solid. Okay. So what we need here is we need our, and remember we want the anode over here. So we want to produce electrons here. So we'll draw on our zinc solid, right, a piece of zinc solid. So this is just a hunk of zinc solid. And then on the other side, we'll have some copper, right, the copper solid. You have to connect them with a wire or something here. Put a voltmeter in between, or a light bulb or something. Just put V for voltmeter. Okay, so they're connected. Now we have to make some solution here, right? We need zinc ions and copper ions. So let's have a solution with zinc ions and another solution. But now we need copper ions. Okay, we're almost there, except if you remember messing around with electrical circuits, you always need a complete circuit. So our circuit is not complete. We need a salt bridge. So we have this gel-like material that's just saturated with salt ions. Okay? So as the zinc solid is producing zinc plus 2, right? The zinc plus 2 is being produced. That means that, let's say we have a lot of sodium ions and chloride anions in here, right? So if we're producing zinc plus 2, chloride anions have to be coming out of here to keep the charge balanced. On the other side, copper plus 2 is reacting, so we're losing positive charge. So we need positive charge coming out of that salt bridge, sodium ions. Okay. So do we have any other labels missing? We should label our cathode. We already labeled our anode and the direction of electron flow. Okay, that's pretty much everything. So when they ask you to draw a conventional voltaic cell diagram, this is what they're asking for. The homework is also going to say, hey, don't draw it, just give me the shorthand galvanic cell notation. So what you do there is you take a look at your half reactions. Zinc solid, I'm going to rewrite them one more time here, goes to zinc plus 2 electrons. That was one half reaction. The other half reaction, copper plus 2 electrons, goes to copper solid. So in the shorthand notation, what we're going to do is we have to have our anode on the left, just like we did before, separated by a salt bridge. So here's my salt bridge. Double line is the salt bridge. And I have to have the half reaction for the anode on the left-hand side. So I have zinc solid and zinc plus 2. And then I write, just don't write the arrow. Then on the other side, I write the copper plus 2 going to copper solid. Okay, there's just one thing left. If these two are in different phases, you're supposed to draw a vertical line. So if they're both solids, you don't draw a vertical line, just put a comma or something. But this one's a solid, the other one's an ion, so vertical line. Again, one's an ion, one's a solid, vertical line. Okay? That is a lot easier than drawing that nice big picture. But it gives all the same information. Zinc solid going to zinc plus 2 is my anode. Copper plus 2 going to copper solid is my cathode. So same information, just a lot briefer. Iron reacts spontaneously with copper 2. Obtain the half reactions for this and then describe a voltaic cell using these half reactions. So when they say describe, let's just do the shorthand notation. Okay, so let's get the half reactions. Iron solid goes to what? Copper plus 2 goes to what? Well, iron solid goes to Fe plus 2. Balance it. We need 2 electrons over here. Copper plus 2 goes to copper solid. Balance it. Now we need 2 electrons on the reactant side. We have 2 balanced half reactions. Let's write our voltaic cell shorthand notation. Double lines for salt bridge. The oxidation reaction on the left. So oxidation produces electrons. That's going to be my top one. Iron solid. Iron goes to iron plus 2. They are in different phases, so draw a vertical line. Cathode, copper plus 2, goes to copper solid. They're different phases, so vertical line. Consider the voltaic cell. Write the half-cell reactions and the overall cell reaction. Make a sketch and label it. Okay, so let's write the half reactions first. We have cadmium solid going to cadmium plus 2. Cadmium solid going to cadmium plus 2. How do you balance it? Just put 2 electrons over here. So we have the same charge on both sides. Remember, add electrons to the most positive side. We have nickel plus 3 going to nickel solid. Right, according to this, nickel plus 3 is going to nickel solid. Balance it, add electrons to the most positive side, 3 electrons. They want an overall reaction, so what we do, remember doing this? Add them up, add up the half reactions so the electrons cancel. So we have to multiply the top one by 3 and the bottom one by 2. Right, then we'll have 6 total. So my electrons, my 6 electrons will cancel. So I'm going to have 3 moles of cadmium solid plus 2 moles of my nickel 3 will form 3 moles of my cadmium ion and 2 moles of nickel solid. So there is my overall cell reaction. That's what they wanted. Now let's make a sketch. So we are going to need a couple beakers. Right? We're going to need a salt bridge. And we're going to need, we need to produce electrons on the anode. Produce electrons. Who's producing electrons? This top reaction is. This is, remember? Anode's always on the left. So we have a hunk of cadmium solid. Right? And that goes through a voltmeter. It's connected to some nickel. Okay, now we need some solutions for our ions. We need cadmium 2 and nickel 3. Okay, we should probably draw our direction of electron flow. That's always left to right, right? The anode always produces electrons. They travel from the anode to the cathode. Okay, all that we're missing is pretty much the ion flow, right? Cadmium is producing cadmium plus 2, so we need something negative to come out like chloride. We need something, and then on the cathode, nickel plus 3 is disappearing. We need a positive charge to replace it, my sodium ions. Okay, so this is my sodium chloride salt bridge. Well, I forgot my solution. A voltaic cell has an iron rod and 0.3 molar iron 3 chloride solution for the cathode, and a zinc rod and 0.2 molar zinc sulfate solution for the anode. The half cells are connected by a salt bridge. Write a notation for this cell. Okay, so when they say write a notation, remember that's our salt bridge shorthand notation. So what was the anode? They said the anode, zinc rod and 0.2 molar zinc sulfate, was the anode. So here's my salt bridge. Zinc rod and zinc sulfate. Zinc sulfate. The sulfate isn't doing anything. The sulfate is there just to get that zinc plus 2, right? Because sulfate has a -2 charge. So I have zinc solid going to zinc plus 2 electrons. There's my anode. There's my oxidation half reaction. So I'd have zinc solid and 0.2 molar zinc plus 2. And you could write 0.2 molar zinc sulfate if you want, but 0.2 molar zinc plus 2 is really all you need. The cathode, I have iron 3 chloride solution in an iron rod. So for the cathode, I have to react with electrons. So my iron 3, they said iron 3 chloride. Don't let that confuse you. That's just an iron plus 3, because each chlorine has a minus. So my iron plus 3 has to react with electrons and produce iron solid. How many would be 3? So I have iron plus 3 going to iron solid. So I have 0.3 molar iron plus 3 going to iron solid. So there is my final answer. There's my shorthand notation. Zinc reacts spontaneously with silver. Describe a voltaic cell using this reaction. What are the half reactions? Okay, let's do this part first. What are the half reactions? We have zinc going to zinc plus 2. Zinc going to zinc plus 2. We have silver ion going to silver solid. We have silver ion going to silver solid. My zinc was a solid. So how do you balance these? Always add electrons to the most positive side. So 2 electrons over here, 1 electron over here. And they want us to describe a cell. So let's do the shorthand notation again. Salt bridge, anode has to be over here. That means oxidation. Which half reaction is undergoing oxidation? Which half reaction is producing electrons? Same story. It's going to be the zinc. So zinc solid goes to zinc plus 2. Right, different phases, so I need a vertical line. And then on the cathode, I have silver ion going to silver solid. So I think the main idea here is to recognize what are the half reactions. And if you can find out which one is the oxidation half reaction, that always goes with the anode. And how do you identify oxidation? Oxidation means oxidation states are getting more positive. Like, do you see the zinc? It starts out at 0, and then it goes to positive 2. So you can think of an oxidation half reaction that way. Or you can think of it as, oh, an oxidation means I have to produce electrons. See, I'm producing electrons. And so that way electrons always flow from the left-hand side to the right-hand side.